Hello everyone, welcome back to rotational motion. So to date what we've talked about is what I would call rotational kinematics, which kind of like translational kinematics means describing the motion. So theta, omega, alpha, how I connect the dots between those. That's what we've mostly been talking about to date. Today we're going to kind of go the next step. So in the same way we learned Newton's laws for translational motion, we're going to learn Newton's laws in quotes for angular motion. So we're going to have to define something to play the role of a force, which is called the torque. We're going to cover Newton's second law, and then we're going to talk a little bit about how these can be applied in situations where you have both translation and rotational motion. So before we get started on that, I just wanted to say a few words. So exam number 2 has been graded. Everything is posted, online, done, basically, so I don't have to hand anything back, which is the nice thing. I just want to say a few words about it. I mean, so in terms of how people did, the average grade, no curve, was 72.1%. The grade distribution looks like what I have on this screen. And I have to say, I was very, very impressed with the results of this exam. So I was kind of expecting, I mean, this is a harder exam than exam 1, just in terms of material. And with the shift to online format, no ability to get partial credit with the long answer problems, I was expecting to, honestly have to curve the heck out of this exam. And you guys, you really blew me away. So this is a very good average grade. It's actually it's a little bit higher than I generally expect on exams. So you guys did great. It turns out there was no need for a curve. Again, 72 is not your final grade. That's the grade for the exam. And the reason that I don't curve it up even higher is that this is what the actual final grades look like today. So about 2/3 of you are getting an A and a B right now, which is fantastic. Average overall grade is about 81%, which is smack dab in the middle of the B range. And generally speaking, people are doing very well in the class. So as I say, good job, everyone. I really appreciate the hard work I'm sure everyone had to put in, studying and taking an exam in an unusual format. Keep it up. There's only one more to go. Exam number 3 during finals period. If you can kind of stick in there, keep listening to the lectures, stay on top of lectures on homework, and take exam 3 the same way you guys did exam 2. You're going to do great. I'm very, very proud of you guys' work, and I'm very pleased to see the results. Anyway, so that's what I had to say about the grades for exam 2. If you had any other questions about exam 2, the solutions are posted. I am happy to answer any questions that are not obvious in the solutions. And besides that, let's go ahead and move back to rotational motion. So as a quick reminder, the general strategy that we have for this chapter is we want to basically connect the dots between rotation and translation. So for every translational type of motion, there's some equivalent in rotation. We've talked about position, and its equivalent is angular position, or theta. Velocity becomes angular velocity, and so on. Today we're going to talk about force, which in the language of rotation becomes this thing called torque. So today we're going to learn about torque. Now torque causes rotational motion. It is the force, in quotation marks, that causes rotational motion. And people tend to get thrown a little by torque for whatever reason. I think, you'll see there's a cross product and people hate cross products. Can't do much about that. But what I will tell you is you guys actually know quite a bit about torque, whether you realize it or not. So let's start to talk a little bit about what's the intuition behind torque. What do you actually already know? So imagine I have a stubborn bolt right here that I need to loosen. And I'm going to loosen it with a wrench. So either I have a small wrench or a big wrench. And the question is, which of these wrenches is going to make my life easier to loosen that stubborn bolt, to cause rotation of that stubborn bolt? So if you think about it for a second, the answer is, of course, I want to pick the big wrench. There's a reason that you always go for the larger tools. The larger tools are better in many ways. And so there's one thing. The big wrench is going to make it easier to rotate that bolt. What that's going to mean in our language is it's able to produce more torque. Okay, good. So next, Imagine the bolt is still stuck. I turn as hard as I can, it's still stuck. So I grab a hammer and I'm going to hit it. I'm going to hit it either at point A, kind of halfway along the wrench, point B near the end, or point C near the end, but hitting inside instead of perpendicular. So which of these is the best way to hit it with the hammer if I want to move that bolt? The answer, as hopefully most of you know, is B. I want to hit it as close to the end as possible and perpendicular to the wrench itself. So perpendicular to the wrench itself. And these are the lessons that I want you to take away on torque. So you intuitively know which of these situations is going to give me high torque. What I want is large radius. I want to hit it very far away with a large wrench, or I want to hit it very far away here with my force. And I want that force to be perpendicular to this radius. So largest torque is caused by large radius and a perpendicular force. We can put that into a little bit of math with this very simple formula. Torque, which we denote tau, is equal to R cross F. So if I have a force, in this case the force that I'm pushing on my wrench with, acting at a distance r from the axis of rotation. So r is the displacement from the axis of rotation. Torque is R cross F. Quick review, because this is where a lot of people will get lost, is the cross product. So cross products aren't that bad. Cross products are a way of creating a vector as a product of two other vectors. So the way it works is the magnitude of the cross product is just the magnitude of the two vectors times the sine of the angle between them. And we'll learn a couple other ways to do this today. It's not new formulas, it's just other ways to do this exact same formula. And the direction is not so bad. You're going to use the right hand rule. So I want everyone to do this. Take your fingers, point them out. So just so you can see what I'm doing, we're going to take our fingers, point them straight out. If this is vector A, I'm going to point my fingers in the direction of vector A. If vector B is, let's say, up in this direction, I'm going to curl my fingers in the direction of B, and my thumb is going to point in the direction of the cross product. So if we go back to our slides here, everyone take your fingers, point your fingers along A, curl them in the direction of B, and your thumb should be pointing, as the thumb in the picture is, straight up, the direction of the cross product. So the cross product is defined by direction, according to this right hand rule, and magnitude, given by this formula AB sine phi. All right, so let's go back to our wrench problem. Torque is R cross F. Remember, R is the vector that goes from the axis of rotation to the point of contact where the force acts. Okay? So torque is R cross F. R cross F. And for our particular problem here, we can try to figure out both magnitude and direction. So actually pretend you didn't see that. I want you guys to think for a second. First off, what's the direction of the torque? Point your fingers along R, curl them in the direction of F, and your thumb should be pointing out of the page. It should be pointing out of the board. Similarly, what's the magnitude? Well, torque is RF sine theta, where theta is the angle between them, but the angle between them is 90 degrees. So what's the sine of 90 degrees? It's just 1. So this is going to be something we're going to see a lot. If the force and R are perpendicular to each other, then the torque is just R times F. So the torque is out of the board by the right-hand rule, and the magnitude is just R times F because the vectors are perpendicular. All right, so the general rule is going to be torque equals RF sine theta, where theta is the angle between them. Sometimes this is the easiest formula to use. If I give you the angle between them and I give you the magnitudes, just plug in, you're done. If I don't, there are a couple other ways of doing this. So there are two other ways of actually just calculating cross product in general, but it's going to be particularly useful for torque. One is called the method of lever arms. So we're going to illustrate this by talking about this force F1, and then I want you guys to think about F2 and F3 after the fact. So the way this is going to work is, imagine F1 is, let's say we're pulling on a string, and it's acting at this particular point on this object. So the line of action of F1 is simply defined by just continuing that string through the object. The line of action of F1, you just continue that straight line through the object. Then you look along that line and you see where is it closest to the axis of rotation, which in this case is labeled O. So O here is the axis of rotation. And then it's a very straightforward formula. The magnitude of the torque is just the magnitude of that force times this distance between the axis and the closest point, which is called the lever arm. Torque equals F1 times L1, the lever arm. And as before, the direction is just going to be by the right-hand rule. There's nothing special about direction. That is always going to be done by the right-hand rule. So I want you guys to take a quick second, look at this particular drawing. I have three forces, F1, F2, and F3. What are the magnitudes and direction of the torque for the three forces shown in terms of the quantities given? All right, so magnitudes, let's start with that. Again, the rule is torque equals F times L. So torque 1 is just force 1 times L1. Torque 2, the magnitude is F2 times L2, where L2 is this lever arm, which is drawn. So I draw my line of action. I look for the distance of closest approach, and that's my lever arm, L2. Now F3 is a tricky one. Torque 3 is still by definition F3 times L3. But notice, when I draw my line of action for force 3, it goes right through the point of origin. So the distance between the line of action and the origin, or the axis of rotation, is just 0. It goes right through there. And so that means that the lever arm, that minimal distance, is just 0. So my torque is 0 for force 3. Forces that are parallel to the radius are 0. Torque. And now let's talk direction. So the direction of F3 is ill-defined because it's 0. Let's talk about F1 and F2. So with F1, what we want to do, let's go ahead and erase this figure here. We're going to start by drawing the radius R1 that starts out at the axis of rotation and ends at the point of contact. And then we simply need to do the right-hand rule. So everyone take your fingers, point your fingers up in the direction of R1, curl them in the direction of F1, and your torque should be out of the page. So out of the page. That's the direction of your thumb. Let's do F2. So again, everyone should draw R2 on your piece of paper. We have F2 drawn, so point your fingers in the direction of R2, curl them in the direction of F2, and you should find that your torque is into the page. And indeed, that is correct. So that's one way of calculating force that works very well. There's another choice which also works perfectly well, gives the same exact answer. It's called the method of tangential force. So this is just a slight variant. Now what I'm going to do is I'm going to forget about my lever arm, so forget about all this shit. I'm just going to draw my radius vector R1 that goes from the rotation axis to the point of contact, and then I'm going to take my force F1. So you may remember that any force can always be broken up into two components. And in this case, I'm going to draw one component that is perpendicular to the radius R1 and another component that is parallel. That's F1 parallel. And we're going to forget about the parallel part. We're going to take the perpendicular part. And then the torque is just going to be F1 perpendicular times R1. Not times L1, but times R1. leave those here for now. So this is the other method. It's called the tangential force method. And again, the thing I want to emphasize is there's no one right way to do it. These will both give the correct answers, as will just doing F1 times R1 times sine theta. What you want to do is you want to practice each of these methods and just figure out which one is easiest. And then many, many times practice the right-hand rule, because that will always give you the correct direction of the torque, or later angular momentum, which is also a cross product. All right, so let's put this into practice. Consider the following situation. So now I have a wrench, and imagine that my wrench has a length of 0.8 meters. The angle is 19 degrees as shown. And I'm going to step straight down with a force of 900 newtons. So what I want you to do, first off, together, is the torque out of the plane or into the plane for this case. Out of the plane or into the plane. So the first thing I want you guys to all do is try to draw a radius vector r that starts at the point of rotation and ends at the point of contact. All right, so here's what it looks like. Starts at the point of rotation, ends at the point of contact. Is ideally a straight line, but I have terrible drawing skills. That's my radius vector, r. Torque is r cross f. F is pointing straight down. And so point your fingers in the direction of r, curl them in the direction of f, and you should see that r cross f is out of the page, which is plus z. So that will be our general convention. If x and y are our normal axes, plus z will be out of the plane of the paper, but I'll always specify that. I'm not going to expect you to memorize it. All right, now the harder one. What is the magnitude of torque? So take a couple minutes, try to figure out the magnitude of torque using your favorite method, and then we're going to see what the answer is. All right, so I'm going to assume everyone's done this at that point. Let's go ahead and draw this figure. So assuming a massless wrench, the free body diagram of the wrench, artist's conception, looks a little something like this. Here's my wrench. We'll assume it's massless, and the only force acting on it is labeled capital F. It's 900 newtons, and it's acting on the end of that guy. The radius vector, so here's my axis of rotation, and the radius vector, r, has length 0.8 meters, goes from the axis of rotation to the point of contact. A brief note, when you are drawing free body diagrams for rotational motion, always make sure you draw where the force acts, because now we see that for torque, it actually is going to matter where the force acts. So in the free body diagrams, always draw where the force acts. Okay, so here we go. We have this force, we have r, and now we want to calculate the torque tau, which is r cross f. And more accurately, we just want the magnitude because, well, we already solved for the angle. All right, so the first thing we know is that this angle right here is, let's call it theta, equals 19 degrees. So first off, can I just say torque is equal to RF sine theta? No. Why not? Theta, as defined here, is not the angle between R and F. Let's go ahead and see what that angle is. So here's R. Here's F, which points straight down. And what I know is that the angle of R above the horizontal is what I called theta, which is 19 degrees. The angle between these vectors, let's call that maybe phi, is theta plus 90 degrees. So one way to calculate the torque is simply torque is equal to R times F times the sine of the angle between the vectors, which in this case, as we said, was theta plus 90 degrees. So that's 0.8 meters times, what did I say, 900 newtons? Look this up just to make sure I'm not lying. 900 newtons times the sine of 90 degrees plus 19 degrees is 109 degrees. And when you plug this in, this will give the right answer, which turns out to be 681 newton meters. Quick side note, what is the units of torque? Well, it's newtons times meters. That's newton meters. Technically speaking, you could also rewrite this as 681 joules, because newtons times meters gives joules. That's not usually done for various historical reasons. So for example, if you're familiar with non-metric systems, torque is often quoted in foot-pounds instead of the non-SI unit of energy. Again, it's because it's usually thought of as a distance times a force rather than an energy. But they're both right, so I would accept it if you were to write joules. Alrighty, so that's one way of getting the torque. Let's see the other two options. So option 2 is the lever arm method. Let's go ahead and do that one together. So remember the way the lever arm works. I'm going to go ahead and redraw my wrench. So this is the lever arm method. The way I'm going to do it is I have my force F, which is acting straight down. I have my radius R, which is right here. And I have the horizontal right here. So what I'm going to do, I'm going to start by drawing my line of action, which is just a line that goes parallel to F, like so. And I'm going to ask, when does it get closest to the axis of rotation? So it gets closest right at this point here, where it passes through the horizontal. And I will label this distance L, the lever arm. Now notice we can do a little bit of trig. If R is that radius, which is 0.8 meters, and L is down here, theta is 19 degrees, then it's adjacent to theta, so that means cosine of theta is equal to L divided by R. That means that L is equal to R cosine theta. And finally, I can just plug that into my formula. Torque is equal to F times the lever arm L, which is F R cosine theta, where theta again is 19 degrees. And if you plug that in, that also turns out to give 681 newton meters, as it has to. Let's do the final method, the perpendicular force method, or tangential force method. So here, all I'm going to do is I'm going to break my force up into two components. So my force was pointing straight down, but remember my radius was coming at an angle of 19 degrees off the horizontal. So what I want to do is I want to break F into something that's perpendicular to that radius. So here's my R vector, kind of imaginary R vector in this plot. I have a component that's perpendicular to that R vector, which I'm going to call F perpendicular. I have a component that's parallel to that R vector, which is F parallel. This angle here is also theta equals 19 degrees. And then again, I just have to do some trig. So again, cosine of that angle theta is F perpendicular over F. That means F perpendicular is F cosine theta. And lo and behold, when I plug that into my formula, torque is equal to F perpendicular times R. That's F R cosine theta, which is the same thing I had before. So again, I get 681 newton meters. All right. So this is going to be the general strategy that we're going to follow. Calculate the torque using just one of these methods. Obviously, I won't go crazy in any future methods. And then just figure out the direction using the right-hand rule. So we're going to keep returning to this particular example throughout the lecture. It's actually a very useful example. Imagine I have a uniform cylinder of mass m radius r placed on an inclined plane. So there are three forces that are going to act on this. Gravity, which I should say gravity you're going to consider as acting on the center of mass. So I have gravity acting on the center of mass. I have a normal force acting between the plane and the ball. And I have friction. So intuitively, is friction going up the hill or down the hill? Well, I know that this ball is going to want to roll downhill. So friction's going to tend to oppose that. I will guess that friction's going to go uphill. But actually, that's something that we're going to have to check. So in this case, it's going to be right, but that won't always be the case. Anyways, here's our guess as to the three forces. And in fact, this is a very good free body diagram for our block. So what I want you to do, if these are the three forces acting on the block, I've labeled where the forces act, I've labeled the length of the forces, that's my free body diagram. What I want you guys to figure out is what is the magnitude of the total torque about the center of mass. So figure out the torque from each of these forces, then add them up. And is this torque into the board or out of the board? All right, so I assume everyone's had a chance to do that now. For those of you who are coming in late, you can always just pause the videos. Don't think that I'm going to expect you to do it in 30 seconds. Hopefully you paused the video, did the problem, and now let's go ahead and do this together. So here's my ball on the incline. Let's call theta the angle here off of the horizontal. And as I drew on the previous slide, there are three forces. There's the normal force. There's gravity, which acts straight down at the center of mass. And then there's friction, which will go uphill. I'll label that just lowercase f because I haven't told you if it's static or kinetic yet. Let's just label it F. Okay, so there are three forces here. I'm going to do my usual thing of defining coordinate axes. So actually, let's go crazy. Let's define x as pointing down the hill. Let's define y as pointing perpendicular to the hill. And z, I will tell you, is going to be out of the board. That's a usual thing. X cross y equals z, so you can always check that. Fingers along x, curl them along y, you get z equals out of the board. So we want to figure out the torques produced by these forces. And we know that torques will generally be in the z direction because they're perpendicular to the plane of rotation. Alrighty, so what is the torque caused by gravity? So think about this for a second. The torque by gravity is just zero. Why is that? Because our axis of rotation is equal to the center of mass. Gravity acts at the center of mass, and therefore r cross f is just zero, because the radius is zero. What about the normal force? What is the torque caused by the normal force? Here, let's just start by talking about the magnitudes of the torques. So again, the torque caused by the normal force is just going to be zero. And the reason for that, if I draw my circle again here, my radius vector for the normal force is going to go from the center to the point of contact. And my normal force is going to go straight in. They're parallel to each other. And parallel forces cannot, well, a force that is parallel to r cannot cause torque. The angle is 180 degrees here. Sine of 180 is 0. So again, the normal force does not cause torque. Finally, let's talk about friction. So friction will cause torque. And now we just have to appeal to our formula. So the one I'm going to appeal to is F times the radius r times the sine of the angle between them. Let's call that phi to disambiguate that from theta, which was drawn above. The radius is given to us as actually just capital R. And what's the angle between the radius vector, which goes like so, and the friction vector? Well, it's just 90 degrees, right? They're perpendicular to each other. So this is a case, as I mentioned, a very common case that we're going to see, where the torque is maximal. It's just frictional force times the radius r. And that's nice, because now we simply have a magnitude F times r, and we just have to figure out for part B, what's the direction. So what's the direction of this force? Let's go back up to our free body diagram. R is pointing down and to the left. F is pointing up and to the left. And so R cross F, torque equals R cross F. We have to calculate the product. We point our fingers in the direction of R, so point them down to the right, curl them in the direction of F, and your thumb should be pointing into the board. So if out of the board is what I call positive Z, that means this is in the negative Z direction. In other words, if I take the Z component of torque, it's the same way I can take the Z component of omega or alpha, I can take the torque. The torque is just negative F times R in the Z direction. So there you go. If you like it, torque as a vector is just 0 in the x direction, 0 in the y direction, negative FR in the z direction. Alrighty, so why do we care about this? Well, we are going to care about this a lot, starting with the following observation. So how does force enter into translational motion? Well, it enters due to Newton. Newton's laws, the second one anyways, is F equals ma. And torque is going to play a very similar role for rotation. So the generalization of F equals ma is torque equals I times alpha. In fact, this is a more general thing. F equals ma is one formula that involves force. Another couple formulas that we're going to see in more detail next time are work equals F delta S, if F is constant. Power is equal to F dot V. Each one of these generalizes for rotational motion. And again, for now, we're going to focus on this effective Newton's laws for rotation, which is torque is equal to I times alpha. So what do I mean when I write this? What I mean when I write this is that applying a net torque. So if I create a net torque, that will cause, the effect will be an angular acceleration alpha. So just like Newton's laws, a total torque is going to create an angular acceleration alpha. And I is just this proportionality constant. So exactly like translational motion, I want you to remember torque creates acceleration, angular acceleration alpha. It does not create omega. Something can be moving in one direction and torque can be in the opposite direction. So an example of this is like our braking car. So if a wheel is spinning counterclockwise, we would call that omega positive. Now if we apply the brakes to slow it down, the acceleration, the angular acceleration, is going to be clockwise, negative. It's going to be opposite omega. So omega will be positive, alpha will be negative. That means that torque will be negative. The net torque will be negative. So net torque causes angular acceleration. It does not cause angular frequency. So just keep that in mind. It's exactly like translational motion in that sense. So here we go. Here's our first good example of this. So we're going to consider a frictionless pulley, but now we're not going to consider an ideal massless pulley. We're going to consider a pulley with a finite mass. So let's say it's a perfect cylinder, mass 50 kilograms, diameter 0.12 meters, and I'm going to pull on a string that comes off it with 9 newtons of force. So I want you guys to take a couple minutes, figure out what is the angular acceleration of the pulley. I want to know both magnitude and direction. And what's the rotational kinetic energy after it's undergone 2 rotations starting from rest? Great. So at this point, I'm going to assume everyone's given this a shot. Let's go over this answer together. So again, let's quickly draw the setup. I have a massive pulley. The mass is m, which I said was 50 kilograms, so it's quite heavy. The radius, capital R, is half the diameter, which turns out to be 0.06 meters. So just a quick side note, because you get some students tripped up by this. Often problems in mastering like to specify diameters, and heck, I might even do it sometimes. Just, be careful. Convert everything to a radius first, because almost all the formulas involve radii and not diameters. Okay, so I have my ideal pulley. And let's quickly talk. What are the forces acting on this pulley? Okay, so here's my pulley I've drawn. Let's draw a free body diagram. So how many forces are acting on the pulley? I'm going to start naming numbers, and I want you guys to stop when you think it's not good. 1, 2, 3, 4. This part doesn't work so well without raising hands, I'm realizing. So forget about that. Let's just go over the answer together. So the answer is 3. I want you guys to be a little bit careful about this. So there's the obvious one. I'm pulling on the string just as before. When I have a pulley and I have string coming off it, the tension in that string is going to act as a contact force at the point where it leaves the pulley. So the tension in that string is going to be this 9 newtons that I pull on it. But there are other forces acting on this pulley. There's gravity, which is going to act at the center of mass. This is no longer a massless pulley. And if I just had these two forces, this pulley would accelerate downwards at a force of T plus mg over m. So I need something to counteract that. And it turns out the pivot is actually going to provide a normal force, which in this case has to be straight up in order to cancel these guys out. Okay, so here is the actual free body diagram. If I ask you to draw a free body diagram, don't forget about mass and don't forget about gravity and normal force. However, as we're of course going to see, the tension is the only one that's going to matter for the torque. So let's see why that is. The total torque, we know it'll be in the z direction, and it's going to be basically gravity plus normal force plus tension. Those are our 3 forces. Those are our 3 torques. Here I mean the normal axes, so x is pointing to the right, y is pointing up, and z is out of the plane. But again, gravity and the normal force act right at the point of contact. R is equal to 0, and therefore torque is equal to 0. So we can forget about those, and the only thing we have to care about is tension. Now quickly, let's figure out the magnitude of the tension force. So the tension force is acting at a radius capital R. It's perpendicular to that radius. Therefore, the magnitude of the tension torque is going to simply be tension times that radius R, which, did I plug in numbers? Let's see. 50-50, let's see. I did not. So torque is tension times R. And quickly, which direction is it going? So the direction of the torque is R cross F. So we point our fingers in the direction of R, curl them in the direction of the tension, and we should get that the torque is out of the board, so plus Z. So the total torque in the Z direction is just tension times R, which we know. Now what about alpha? Well, we know that the total torque, or the total tension, the total torque in the z direction is I times alpha in the z direction. And we just solved that the total torque is T times R. So if I want to solve for my angular acceleration, it's pretty straightforward. I divide through by my moment of inertia. I get alpha z is equal to TR divided by I. I know everything here except for the moment of inertia. Here I just have to go to that handy dandy lookup table. And what you may remember is for a solid cylinder, we're going to use this a lot, the moment of inertia is 1/2 mass times radius squared. So when I plug that in, I get 2tr over mr squared. One of those r's cancels. I get 2t over mr. And when you plug in those numbers, that turns out to be 6 radians per second squared. So I accelerate at a constant positive acceleration of 6 radians per second squared, which makes sense because it's counterclockwise. Remember, counterclockwise is positive. Let's try that word again. Counterclockwise, which I will abbreviate CC because apparently I can't write it. And so now part B of the question asks, after it's done 2 rotations, or revolutions, those are used interchangeably, what is the kinetic energy? So again, if you didn't solve this part of the problem yet, take a minute, give it a shot. And now we'll go over the answer together. So here it's a constant angular acceleration, meaning that I want to simply solve the formulas for constant angular acceleration. So here we have an initial state where it's at rest. So omega z initial is 0. Let's say the angle initially is 0. I'm just going to define it like that. And at the end of the day, I don't know my final angular frequency, but I do know that I've undergone 2 rotations or 2 revolutions. And if I want to convert that into an angle theta, all I need to do is say that 2 pi radians is 1 revolution. So I do a units conversion, my revolutions cancel, and I get 4 pi radians is 2 rotations. Alrighty, so then I just go into my formulas for constant angular acceleration. The one we're going to use is delta omega z squared is equal to 2 alpha z delta theta. So that's omega z final squared minus omega z initial squared is equal to 2 alpha z delta theta. And I should say delta theta is theta final minus theta initial. Theta initial is 0. Omega z initial is 0. So omega z final squared is just 2 alpha z times theta final, which I could plug in, but I'm not going to. The problem doesn't ask for this, it asks for the kinetic energy, but that's pretty straightforward. So the rotational kinetic energy, notice there's no translation, so it's just rotational, is 1/2 I omega squared. So that's 1/2 I, we said was 1/2 mr squared. Omega z squared is what we just solved for, 2 alpha z times theta z. And now if we plug in all these numbers, what we get is 6.79 joules. So that's the rotational kinetic energy at the end of the day. All right. So there we go. Now we can solve similar problems like this. We'll do some of these on the homework. The thing to remember here is torque causes angular acceleration, and then it's pretty straightforward. It's kind of like Newton's laws. You solve for the torque, you solve for alpha, and then you just go forward and use your constant acceleration formulas. Now the reason that rotational motion is a little bit more complicated often is that it comes in tandem with translational motion. So imagine the following situation. Let me see if I can demonstrate this with my, I'm not going to do this with my Apple Pencil. I'm too cheap to do that, and I'm definitely too bad at catching. Let's see if we can do this with one of the cheaper items in my room. Gosh, my phone is so cheap, but I don't want to do that. Oh, here we go. I have a crappy pen over here. All right, so with this pen, I can do rotational motion. So imagine I actually had a really good axis. I could rotate it around any given axis. My fan up there, rotational motion. I could do translational motion. I throw it up and I catch it. But then, as you even saw in my crappy version of rotational motion, of translational motion there, it's not even easy to do just translational motion. The most common thing is both. it's rotating while it undergoes some translational motion, in this case free fall. Okay, so there's rotation plus translation at the same time. And for the majority of the problems we're going to solve in this class, it's going to be both. It's not going to be one or the other, it's going to be both. So here is that same example basically. So imagine I toss a baton. Well, imagine someone that's skilled tosses a baton. What it's going to do, it's going to undergo the same kind of motion that my pen just did. It's going to undergo parabolic motion of its center of mass while at the same time rotating. So this has translational and rotational motion at the same time. And these problems aren't actually so bad. The thing you should remember is just do them independently. Do them independently and only connect them at the end of the day. Okay? So the way to think of that is the center of mass, just treat it as a little point. And that center of mass is just going to undergo standard trajectory parabolic motion. It's just F equals ma for the center of mass. And then around that motion, there's just going to be rotations. So you're going to rotate around that trajectory. So it's translation of the center of mass plus rotation around the center of mass. And notice throughout the slide I keep saying center of mass. Center of mass plays a very important role in these types of problems. It's your natural axis of rotation. So the best way to always do these is treat the center of mass as the axis of rotation, and then its acceleration is going to be just F equals ma. Its angular acceleration about the center of mass, the moving center of mass, is torque equals I times alpha. And all of our other formulas work as well. So for example, kinetic energy, what I do is I just add up translational kinetic energy, 1/2 mv squared. V here is the velocity of the center of mass, plus 1/2 I omega center of mass squared. So those two together are the total kinetic energy of my problem. Okie dokie. So that's how we're going to do translation plus rotation treated together. And now what I want you to do is I want you to go back and think about our previous example. So this is the same thing. I have a uniform cylinder of mass m, radius r on an inclined plane. I don't think I labeled it, but here this angle we're going to call theta. And from earlier, what we figured out is that the torque is out of the plane, into the plane, which is the negative z direction, and it has magnitude F times r. So go back to our free body diagram, which had gravity pointing straight down, a normal force pointing up like so, and friction pointing up the incline. And what I want you to do is take a few minutes and figure out what's the angular acceleration of the cylinder, what's the linear acceleration, and at the end of the day, I want you to ask, is A equal to alpha times R? Why or why not? All right, so let's assume you've had a chance to do this problem. Again, it's one of the more complicated problems we do. I mean, it's a pretty standard one, but it's not a particularly trivial one. But if you just use the rules that I've taught you, it really doesn't need to be that much harder than any of the previous problems that were a little bit simpler. So just a few more pieces to add together, but none of them is actually that much different. All right, so again, this is the problem we have here. I'll draw the free body diagram. I have the weight pointing down. I have the normal force, which is perpendicular to the plane, and I have the friction force, which points up the plane. From earlier, we saw that the torque in the z direction is just due to friction, and its magnitude is negative F times r. So part A asks us, what is the angular acceleration? Well, that's pretty straightforward. I just use torque is equal to I times alpha in the z direction. I want to solve for alpha z, so alpha z is negative Fr divided by I. And if I wanted to, I could make the substitution, my moment of inertia I, for a for a cylinder, which is what I think I specified in this problem, is again a half mr squared. You'll notice I like to use this a lot, but it's not really that special. It's just one I used. And so if I like, I could also rewrite this as negative 2f divided by m r, where f is the friction force. So there you go. That's my angular acceleration alpha. Notice it looks pretty similar to the previous problem. Now force of friction is the only thing doing torque, but otherwise it's, the same. All right, so part B of the problem now asks, what is the linear acceleration? So here, don't make it complicated. This is the linear acceleration of the center of mass. All we're going to do is we're going to use usual Newton's laws. So if this guy is our free body diagram, I'll do my usual choice of axes, which is the same thing I did when I was doing this problem earlier. So x is downhill, y is perpendicular to the hill. And now there's only one force that I need to break up into the components, which is weight. Okay? So my weight is pointing straight down. I want to break it up into a perpendicular component, a component that points in the negative y direction, a component that points in the positive x direction, so wx, wy. You can do a little trig or a little geometry, figure out the small angle here is theta. And now I just do my usual trig. So in this case, wy is mg cosine theta. Wx is mg sine theta. And I can just redraw that free body diagram. It's a circle, but it doesn't really matter at this point because I'm just doing linear motion. So here's my, there's my ramp. So I have mg sine theta pointing downhill. I have mg cosine theta pointing into the hill. I have an unknown normal force pointing perpendicular to the hill. And I have force of friction, which I don't know, F pointing uphill. Now the acceleration in the y direction, as always, is 0 because it doesn't accelerate into or out of the hill. The acceleration in the x direction, I just have to use Newton's laws. So the total force in the x direction is equal to mg sine theta, which points downhill in the positive x direction, minus friction F, which points uphill in the negative x direction. And that's just mass times acceleration, ma. So if I want to solve for my linear acceleration, I just divide through by m. I get that ax is equal to g sine theta minus f over m. And since I didn't give you any particular numbers, we're done. That's my acceleration down the hill. So the final part of the problem asks, is acceleration equal to alpha times r? So I told you under certain circumstances, it will be the case that at least the magnitude of acceleration is equal to alpha times r. However, this is not one of those cases. You can just convince yourself of this pretty straightforwardly. So here's my acceleration. I'm just going to copy that. Here's my alpha. They look nothing alike at all. There's an f over m. That's about the closest thing. In fact, alpha has nothing to do with theta. It's completely gone from the problem. So there's no way that this guy will, in general, have a equal to alpha times r. And that turns out to be correct. In general, it will not be the case that an object rolling down a hill will satisfy a equals alpha times r. So this is really hard to see because we're kind of used to situations where the answer is yes, but it's not actually that crazy. So imagine the following scenario. Imagine I had, I don't know, where can I construct a ramp in this room? Okay, good. So I'm going to construct a ramp out of my keyboard here. I think I need to point this guy a little further down. And on this keyboard ramp, what we would be used to is the following situation. If I just took, maybe not my pen, but for the lack of circular objects, I must. Okay, well, I'm going to take my pen and I'm going to simulate a usual system. So a usual system would roll like so. And you'll notice that as it rolls down, it's rotating. The distance it rolls is equal to 2 pi r. So when I do one revolution, I trace out the circumference. But that's not generally the case. For example, if there were no friction, there isn't actually not a lot of friction here. So if I just take my pen and I drop it, it's probably way too fast, but what you might have seen is that it's just going to slide down without rolling. There's not enough friction there to cause it to rotate. If I did this with a rubber ball, it would start to rotate. So if there's not enough friction, it's going to slide down. The general property is if there's a little bit of friction, it'll rotate a little bit. It'll do more sliding than rotation. And so if it's doing more sliding than rotation, it will not generally be the case that acceleration is equal to alpha times r. You want to be really careful about that. So people tend to make that mistake a lot. All right, so here it is not the case that a equals alpha times r. That's in fact generally not the case. However, there is a special case where this is true, and it has a special name, and it's going to be almost the entirety of tomorrow's lecture, of Thursday's lecture. So the special version where velocity is equal to r times omega, a is equal to r times alpha, etc., is called rolling without slipping. If the rotation satisfies the special property that the velocity of the center of mass is equal to r times omega, then it is called rolling without slipping. All right. So we're going to see there are a lot of very nice properties here. The first one I want to demonstrate by just tracing out what's happening. So if you think about this, as I told you, I can always break up my motion into translation plus rotation. So if you just look at the translation, it looks like what I've drawn here. Each of the points moves together at a constant velocity, which is the velocity of the center of mass. If you look at just the rotational bit, it's rotating in this case clockwise because my motion is to the right. And so what that means is at the top, my velocity is pointing to the right, and it's equal to v center of mass because r times omega is equal to v center of mass. So omega is how fast I go, r is this distance. Again, I get the velocity of center of mass pointing to the right up here. Over here, it's pointing up. Over here, it's pointing down. And notice at the bottom, the rotational part has the velocity pointing exactly to the left with magnitude equal to the speed of the center of mass. So now, what's my general motion? I just add these two guys up. Okay, so you do vector addition of these velocities. At the top, I have VCM plus VCM equals 2 VCM. So it moves very fast to the top. On the sides, I have something pointing right plus something pointing up. Gives me something pointing up and to the right. This is down and to the right. And now notice the bottom. At the bottom, the translation is moving right. The rotation is moving left with the same speed. When I add those two up, I get 0. So there's this really crazy property of rolling without slipping, which is the point at the bottom is instantaneously at rest. It is temporarily not moving. And that's kind of crazy. It turns out this bizarre fact also has some really important implications. So the point in contact with the ground is at rest. That means that it experiences static friction. So remember, if I have friction on a non-moving object, that's static friction. And static friction, you may remember, is a conservative force. So the work done by static friction is the force of friction times the distance, but if it's not moving, the distance is 0. Which means the work done by friction is always, static friction is always 0. It is a conservative force. I can write down a potential energy, which is just 0, but still. And what that means is that for rolling without slipping, energy is conserved. Rolling without slipping is going to be the special condition where V is equal to R times omega, A is equal to R times alpha, and energy is conserved. So that's going to be a lot of our lecture next time, is using the properties of rolling without slipping to solve for motion with conservation of energy. Notice that when I talk about energy conservation, I will sometimes have to talk about gravitational potential energy. You will always calculate that from the center of mass. So gravitation acts at the center of mass, and the gravitational potential energy is the height of this mg times the height of the center of mass. So rolling without slipping is energy conserving, and it will allow us to connect linear and rotational motion via these formulas. So I'm going to leave you with the following example. We will not solve it today. We're going to solve it on Thursday. But consider the following situation. I really, really regret that I can't go into the office right now because I love this demo. Found the best video I could, but it's not quite as good as the demo. But I want you to, if you guys have spools of thread around your house, like crappy spools of thread in a sewing kit, if I can find one, I'll record just a very quick version of this and then upload it. But I want you to try this. So first, wrap it so that the spool comes off the top, as is drawn on the left-hand side here, part A. So I want you to think, if I pull on that, which direction is it going to move? All right, so imagine I do the following. It rolls without slipping, which is the usual thing with the presence of friction. Which direction is this guy going to go? Right or left? So I think the intuition here, which is correct, is that it's going to move to the right. Here we have a quick demo video that's a little backwards, unfortunately. But if we go to our demo here, I guess it's not in this. I guess it's in Safari. So here's that exact spool. And what they're going to do, it's very hard to see, but there's a string coming off near the top to the left. They'll draw a little arrow in a second so you can see which direction the spool is going. And indeed, when they pull, it's going to move to the left. All right, so let's see that one more time. I have a piece of yarn coming off the top of this spool. I pull to the left, and it goes to the left. All right, so now let's imagine the opposite situation. Part B, I'm going to thread that spool off the bottom. So the question is now, does it move left or right? Let's see. So here we go. It's a little hard to see, but it's kind of the same spool. And right now the thread is coming off of the bottom. It's a thin red line that's kind of on the gray area floor there. So it's going to go to the right as well. All right. So in both of these cases, it's actually a little counterintuitive. It's always going to go in the direction of the force. And so next time we're going to pick up by calculating the torque, the acceleration, and then connecting them using rolling without slipping to solve this problem. All right, have a nice couple of days. Everyone stay safe, and I will talk to you soon.